in this video, we're going to talk about 5 different ways of proving triangles are congruent. And those 5 ways are this. We're going to talk about each of these cases, starting with these 4. And basically, you can see how we only need 3 parts to the triangle in each of them. Now, if triangles are congruent, then that means they're unable to change. We're going to show that a specific combination of any of these parts is always going to produce a fixed triangle. So starting with SAS, let's say we have something that looks like this. We have a side, some specific angle, and a specific side. So basically, this is a side, an angle, and another side. And based on SAS congruence, for a given triangle, this side length, this angle, and this side length must be fixed, right? They can't change because we know what they are. Now, what that means is, intuitively, it's impossible to really bend this structure that we have here. So no matter what, we're forced to construct a specific side length between the 2 endpoints, which results in only one specific triangle for this combination. So if we had another triangle with this combination, for instance, we reproduce this side length, we reproduce this angle, and we reproduce this side length, right? Pretending that this is basically identical to it, we're forced to construct that same line that we're constructing here, resulting in a congruent triangle. Now what we're going to do is look at ASA congruence. Basically, we got to imagine that we have some angle that we know. So this angle, we have a specific side length and another angle right here. So we know this angle, this side length, and this angle. So this angle, whatever the angle that's being formed right here, is going to be fixed. This side length is going to be fixed, and this angle is going to be fixed. Well, what that means is we are forced to construct dashed lines in this direction because the angle fixes this direction in place. And same thing for this angle. It has to fix the direction in this place. So no matter what, we're forced to construct a triangle that looks like this. As you can see, with a given angle, side length, and angle that appears this way, we are forced to construct this triangle right here, which gives us only one possible triangle for ASA congruence. And that's the whole idea. So no matter what, if we were to reproduce another triangle, we're going to get the same exact formation. It's going to be this same exact triangle. SSS and AAS, the intuition is a little bit more difficult, but we're still going to see how it works. For SSS, what this really means is if we know the 3 side lengths of a triangle, then there's only one triangle that it can be. So a combination of side lengths such as 3, 7, 9, if we know the side lengths of a triangle are 3, 7, and 9, then we're only able to produce one triangle from this set of side lengths. Or if we had the side lengths 5, 5, and 5, only one triangle can be produced with this set of side lengths. Or if we had 3, 4, and 5. It turns out that we can only produce a right triangle from this setup. If you recall, 3, 4, and 5 are Pythagorean triples, so you can kind of see why. For 5, 5, 5, we can only produce an equilateral triangle from this. For 3, 7, and 9, only one type of triangle we can produce. So then how can we gain an intuitive understanding from this though? Well, here's how we can think about it. Let's think about our 3, 7, 9 example. The way that I like to think about it is we take our longest side and construct it as a horizontal line. So let's say that this is our side length 9. And really, the way that we're going to think about it is the fact that there's only one possible way to construct the other 2 side lengths. For instance, if we draw the side length of 3 like this, then we have to construct the side length of 7 like this. Because if we were to, let's say, rotate the side length of 3 like this, let's say we were to reconstruct the side length of 3 like this, still a side length of 3, but it's impossible for us to construct the side length of 7 there. Or let's say we were to construct the side length of 3 going in this direction like this. Well, then the side length of 7, if we were to rotate it, it's going to be too long. So there's only one way to really construct this side length of 3, which is just like that. Now, it is true, yes, if we were to construct the triangle a little differently, where we started with the 7 on this side and the 3 on this side, but as you can see, it doesn't change the triangle that we have. It just basically flips it around. Next, looking at AAS congruence. Basically what AAS means is we know an angle, we know another angle, and we know this side length right here. Now, here's the thing. This side length is different from what we had in ASA, because this side length is not between the two angles. What you really have to see from a setup like this is the fact that we don't know if this side length can vary or if it's fixed in place, right? We're going to prove that this side length is actually fixed in place. Because notice, if we are forced to construct a dashed line in this direction because the angle fixes that direction in place. So we're forced to construct a dashed line there, but notice how it does not connect with the endpoint right here. We have to connect this dashed line with the endpoint, however, because this side length is fixed in place. And this angle is fixed in place, so we know that this endpoint is going to be located here no matter what. So in order to make this dashed line actually intersect right here, the only thing we can do is change this length of this side. In fact, we got to make it longer. And if we were to do that, about right here, right, this angle right here cannot change. We should be able to find a specific location for this angle such that it intercepts with the endpoint right here. So you can see there's only one specific side length that this can be in order for us to construct that endpoint, which means that this side length right here is fixed. And because we know that the angle, side, and angle are fixed, we know that this becomes ASA congruence. So that gives us the intuitive understanding for AAS. All right, so the last case where we have to look at is HL. HL is only true for a right triangle. There's really three things we're given. We're given a hypotenuse, leg, and right angle. Now, here's the thing. This representation, the hypotenuse, leg, and right angle, is none of the four that we have right here. In fact, this is actually a side length, and an angle. But it's not side, angle, side, because this angle is not between the two side lengths. Now, here's the thing about HL congruence. The reason why it's true is because if we know the hypotenuse and leg of a right triangle, we're always able to find what this other leg is by using the Pythagorean theorem. For instance, if the hypotenuse length is 5 and the leg is 4, right, these two side lengths are fixed in place. But we can always use the Pythagorean theorem to find what the other side length is. And you're going to find that this other side length is 3. And the only possible number for this side length is 3, which means that this leg is also fixed in place. So that means that this triangle is fixed in place by side, side, side. So HL really becomes side, side, side. So this gives us the intuitive understanding of HL congruence. And really, in this video, we showed that each of these combinations gave us a fixed triangle. And if we have a fixed triangle, we're only able to reproduce one triangle from any of these three combinations. So we're always going to get a congruent triangle if we have one of them. And so this is the whole idea of the intuition behind each of these 5 cases. And that's pretty much it.